Glass, the backbone of every city, every screen, every bottle on a shelf, begins as nothing more than ordinary sand. Yet, every year, megafactories convert over 130 million tons of this raw earth into flawless sheets, intricate bottles, and fibers thinner than a hair. Beneath the calm exterior of molten glass, this process demands unrelenting furnaces reaching 1,650 degrees and the kind of chemical precision where a single impurity can ruin an entire batch. So how do billions of sand grains survive this intense transformation and emerge as the glass that shapes our world? The answer is far more dramatic and vital than you might imagine. Inside every megafactory, glassmaking begins with a precise blend of ingredients measured in tons, but calculated down to the smallest fraction. Silica sand forms the backbone, about 70 to 73% of every batch. Only the purest quartz sands, often refined until they reach over 99% silicon dioxide, are chosen for float glass and optical products. Even a trace of iron can tint the final pane green or brown, so mines scrub, wash, and test each shipment, discarding grains that don't meet the mark. Soda ash is added to lower the melting point, making it possible to melt the mix at temperatures that, while extreme, are still manageable for industrial furnaces. Limestone strengthens the finished glass and reduces its tendency to dissolve in water, crucial for windows and bottles that must last for decades. Mixed in with these raw materials is cullet, or recycled glass, making up a quarter to nearly a third of the batch. Cullet melts more easily, saving up to 40% in energy, and helps glassmakers recycle their own waste back into the process. This careful recipe is the foundation for everything that follows, setting the stage for the intense heat and transformation inside the furnace. Deep inside the heart of the factory, the continuous furnace roars with a power that never sleeps. This industrial giant stretches the length of a city block and holds up to 1,200 tons of molten glass at any moment. A reservoir of liquid fire. Temperatures inside climb to 1,650 degrees Celsius, hotter than the surface of an erupting volcano. The plant manager, acting as both engineer and sentinel, monitors every gauge and sensor from the control room, making critical decisions that keep the furnace stable. Here, the rhythm is relentless. Raw materials and cullet are fed in at one end, while a river of molten glass flows out the other, day and night, for up to 15 years before the furnace is rebuilt. Gas and oxygen burners, sometimes aided by electric boosters, maintain the inferno with precision. Any lapse, a blocked burner, a sudden drop in pressure, could threaten the entire operation. The unbroken cycle of melting, 24 hours a day, is what allows megafactories to produce millions of tons of flawless glass every year. Once the raw batch has melted into a river of glowing liquid, the next challenge is purification. Tiny bubbles and streaks can ruin the strength and clarity of finished glass, so technicians add fining agents like sodium sulfate directly into the melt. These chemicals trigger reactions that help trapped gases rise and burst at the surface, leaving the glass as flawless as possible. The entire mass is stirred and sampled, every movement calculated to guarantee uniformity. Even at this stage, the temperature is carefully managed. If it cools too quickly or stays too hot, the glass can become brittle or too viscous for shaping. Gradually, the molten glass is cooled to around 1,000 degrees Celsius, just right for forming. At this point, it's channeled through a system called the forehearth, which delivers a steady stream of perfectly conditioned glass to the forming lines. Only after this careful refining is the material ready to become anything from skyscraper windows to everyday bottles. With the molten glass primed at just the right viscosity, the next act unfolds on the forming lines, where a single river of glass splits into 3 distinct destinies. For float glass, the Pilkington process takes center stage, Here, a glowing ribbon pours onto a bath of molten tin, kept under a protective atmosphere of nitrogen and hydrogen. The glass floats effortlessly, spreading out into a perfectly flat sheet, its underside untouched by air or roller. Every meter, the chemistry above the tin keeps oxidation at bay, while operators monitor sensors and occasionally skim away tin oxide dross with specialized paddles. As the ribbon cools, it travels forward, gradually solidifying before robotic blades slice it into panels as long as a city bus. Meanwhile, container glass follows a different choreography. Molten gobs, each precisely cut, drop into cast iron molds. High-speed machines inject bursts of compressed air, shaping the glass into bottles or jars in a matter of seconds. Each mold cycles thousands of times per hour, synchronized to a relentless mechanical rhythm. For fiberglass, the process is even more dramatic. Molten glass is forced through bushings with hundreds of tiny holes, forming threads thinner than a human hair. In these lines, machines are the silent performers, guiding every drop and fiber into shape with unwavering precision. Freshly formed glass, still warm from the shaping lines, enters the annealing layer, a tunnel stretching the length of a freight train. Here, the temperature drops in carefully measured steps, sometimes over several hours, depending on the thickness of the glass. This slow, controlled cooling relieves internal stresses that could cause spontaneous cracks or shattering down the line. Conveyor belts move each sheet or bottle at a steady pace, ensuring every piece experiences the same gentle gradient from red hot to room temperature. Once annealed, the glass is stable but still unfinished. On the cutting floor, finishing line crews operate diamond-tipped blades and computer-guided lasers, slicing massive ribbons into precise panels or trimming bottlenecks to uniform height. Edges are ground and polished until they're as smooth as river stones, safe to handle, flawless to the touch. In a separate chamber, technicians apply advanced coatings. For architectural glass, a whisper-thin low-E layer is vapor deposited, reflecting heat while letting in light, transforming each pane into a barrier against summer heat and winter cold. These finishing touches prepare the glass for its final test, quality inspection, where only perfection passes. Inside the inspection hall, glass panels and bottles move in perfect formation beneath a gauntlet of sensors and high-speed cameras. Every square centimeter is scanned by optical systems, their lenses tuned to spot the tiniest imperfection, bubbles, streaks, or microcracks invisible to the naked eye. For float glass, line scan cameras and lasers measure surface flatness and thickness down to a few microns, ensuring that each ribbon remains flawless from edge to edge. Container glass, shaped into bottles and jars, rotates under area cameras, while infrared and X-ray scanners peer beneath the surface, searching for hidden inclusions and internal stresses. AI-powered algorithms sort through millions of data points in real time, learning to recognize patterns and flagging defects that might escape even the most experienced human inspector. Any piece that falls outside the strict tolerance is automatically diverted, destined for recycling. The quality engineers oversee these systems, trusting their precision to uphold standards that allow glass to withstand pressure, weather, and time. Only after passing this battery of tests is a sheet or bottle cleared for the world beyond the factory walls. Every year, glass factories worldwide produce nearly 130 million metric tons of glass, enough to wrap the planet in windows, bottles, and screens many times over. This staggering output relies on a powerful advantage: recycling. By adding cullet, recycled glass, directly into the batch, factories can cut energy use by up to 40%. Less energy means fewer emissions, lower costs, and a smaller environmental footprint for every ton of glass made. The more cullet in the mix, the more efficiently the entire process runs. In a world demanding both performance and sustainability, glass manufacturing stands at the crossroads of scale and responsibility. Glass is entering a new era, where technology and sustainability go hand in hand. Smart glass panels now adjust their tint with a tap, using electrochromic layers to block sunlight or let it in on demand. Flexible glass, thin enough to bend without breaking, is opening doors for foldable screens and curved displays. In the furnace halls, engineers are testing hydrogen and electric boosters, cleaner alternatives that could cut carbon emissions to near zero. On the recycling lines, artificial intelligence sorts scrap glass by color and purity, making it easier to reuse every shard. These breakthroughs are reshaping what glass can do and how it's made across megafactories worldwide. Every year, the world's glass factories produce over 130 million metric tons of glass, an output made possible by high-purity silica sand, 1,650-degree furnaces, and precise automation. This documentary has shown how ancient techniques evolved into today's continuous flows, from the Pilkington float process to automated inspection systems that check for defects down to the micron. While the chemistry and engineering are well documented, some details, like the exact recipes for specialty glass or proprietary furnace controls, remain industrial secrets. What is clear from decades of research and industry data is that recycling cullet saves up to 40% of production energy, and next-generation technologies like smart glass and hydrogen furnaces are gaining ground. As new innovations emerge and sustainability becomes more urgent, glass remains a silent foundation of modern life, linking the raw materials of the earth to the structures and tools we depend on every day.